Continuing 8.1, Soil and Hazards. Soil texture. For demonstration purposes, I have a soil with 50% sand, 30% silt, and 20% clay. Now my graph line will parallel the axis to the right. I will start with clay. 20% on the clay axis is here. My line will parallel the axis on the right, which is the sand axis. The other end of my ruler will go straight across to 100 minus 20, which is 80 on the silt axis. I draw my line all the way across. Next, I will graph my silt percentage, 30%. My line will parallel the axis to the right, which is the clay axis. My ruler will go straight across to the 100 minus 30, which is 70 on the sand axis. Where they intersect is my soil texture. In this case, loam. But I will also graph my sand percentage just to make sure everything works out okay. And it does. Okay, your turn to try. Here's the percentages. Sand, 30%, silt, 60%, and clay, 10%. Pause the video and graph it, perhaps in pencil on the soil texture figure in your book, or print a copy from online. When you've got it graphed and the soil texture identified, see if your answer matches mine. Here I go. Soil texture. Soil texture is silt loam. Could you maybe do this on a test? I sure hope so. To be sure, here's another soil with 70% sand, 70% sand, 5% silt, 25% clay. Pause and graph it. Did you get sand, clay, loam? I hope you did. Questions? Perhaps replay the video. Still don't get it? Ask for help. Soil structure depends on PEDs, soil particles that cling together in aggregates. Types of structures include granular structure, blocky structure, prismatic structure, and platy structure. These structures are depicted and described in the chart below. I know the soil structure is useful for understanding the strength, drainage, and nutrient characteristics of the soil. Relative soil profile development will give information about the recent history of an area, including information about natural hazards that may have disturbed the soil. A soil chronosequence is a series of soil developments, combined with numerical dating such as carbon-14 decay and exposure dating. The youngest soil development example is a weakly developed soil with an A horizon directly over a C horizon. This type of soil development is typically a few hundred to several thousand years old. My images have some profile examples. The cartoon on the bottom left is of several soil profiles. The relative age of these soil profiles, assuming they are all from the same area, goes from youngest on the left to oldest on the right. See how as the soil develops, more soil horizons are visible. And the image on the bottom right is the closest real example I could find of an A horizon directly over a C horizon. A moderately developed soil has an A horizon overlying a BT horizon that overlies the C horizon. The BT horizon is not as red as it could be, given more time. It may have more of a yellow color. It has not had much time to accumulate the iron oxides that make it more red. It has not had sufficient time to accumulate much clay, silica, or other carbonates either. But it is definitely a good beginning of a BT horizon. This moderately developed soil profile is more than 10,000 years old, so at least Pleistocene in age. So back to the Ice Age for moderately developed soil. The image on the bottom left is the relative soil profile development cartoon, and on the bottom right is an image of a moderately developed soil profile. A well-developed soil has a BT horizon that is more red, and there is more translocation of clay to the BT horizon and stronger structure. The soil is between 40,000 and several hundred thousand years, and perhaps even older. Best to get a firmer date on that with some carbon-14 or exposure dating. The images are again the same cartoon on the bottom right, showing relative soil profile development. And on the bottom right, we have a picture of a soil profile with A, B, and C horizons, a well-developed soil profile. As the soil develops even more, the light-colored E horizon appears. It takes time to develop a nice leached layer. Moving on to water in soils. My favorite. Moisture content is the amount of water in a soil. Water increases strength of soil up to a point, and the degree of saturation of the soil determines if there is saturated flow or unsaturated flow of fluid from the surface to groundwater reservoirs in the subsurface. So let's look at the image. We've got a super blown up structure of soil particles and water and air. So remember, these soil particles are actually very small. The biggest are 2 millimeters in diameter. The smallest are way smaller. The space between the soil particles can be so small, only like a molecule of water fits between. This is a small space, but it is an important space. The attraction between water and soil, due to polarity of molecules, can help keep soils stuck together up to a point. As soil dries out, this water-soil attraction can be lessened, and the soil becomes weaker. Also, you can imagine, I bet, that water has a much easier time flowing through the soil if there's already water there, as opposed to having to push around large obtruding pockets of air. So soil moisture definitely affects how easily water can percolate into the ground. Does this sound familiar from another hazard chapter? Maybe the flooding chapter? Maybe you might remember that this is very relevant to flash flooding. Soil classification is different from soil scientists and for engineers. The soil taxonomy used by soil scientists is based on physical and chemical properties of soil profile. There is a six-fold hierarchy with order, suborder, great group, subgroup, family, and series. This method of soil classification is useful for agricultural and land use. Several soils are listed in a table in your book, and you can find much more detailed soil taxonomy online. I have used soil maps to investigate soil moisture problems, especially near lakes. These maps used soil taxonomy classification. Another method of soil classification is the Unified Soil Classification System, often used by engineers. It is based on particle size or the abundance of organic material and is generally used to evaluate hazards. You can find a sample table for this method in your book, or you can easily find a much more complete table online. When I worked in environmental consulting, we used this method to classify soil samples and soils where we installed piezometers and wells. So, takeaway message, if you're going to do stuff with soils, you will come across both classification systems, and both are useful. Soil erosion as a hazard is sometimes overlooked. Soil takes a long time to develop, hundreds of thousands of years in some areas. We use and need soil especially for agriculture. However, we lose soil through erosion. As soil is lost faster than it can be replenished, even in areas where soil erosion is minimized, poor agricultural practices combined with prolonged drought is what caused the Dust Bowl catastrophe in the 1930s, where 100 million acres were affected. In some areas, more than 75% of the topsoil was blown away, permanently degrading the agricultural value of the land. Since then, we have adopted agricultural practices that better protect the soil. We know from history that soil erosion has toppled civilizations as agriculture became impossible, which proves how important it is to safeguard our soil. Below is an image I often see around here. Someone plowing their field while it's windy. Easy to see the soil erosion. Hard to know how to stop the wind. I hope they mitigate the soil erosion hazard, perhaps by replenishing and rebuilding the soil with some manure. 8.2 Introduction to Subsidence and Soil Volume Change. Subsidence is ground failure characterized by sinking or vertical deformation of land associated with soil. There are several types of subsidence. First, we will discuss the dissolution of rocks beneath the surface, which results in karst topography. In the images below, we have two examples of karst topography. The image on the left of west central Kentucky with several little pockmarks, each a sinkhole. The image on the right is from China, with the towers, and the towers are all that is left of the eroded cave system. All those collapsed sinkholes just left the towers. Both landscapes formed as water slowly dissolved the carbonate rock, mostly limestone, along cracks and fractures. As the dissolution continued, the cracks became caves, and still dissolution continued, and perhaps the water table lowered, and the cave could no longer support the roof, which collapsed, forming a sinkhole. Which image is the more advanced karst topography, meaning more dissolution has occurred? Right, the right one. We will talk more about some interesting hazardous and useful karst features in a little bit.